Okay, let's go ahead and get the backup recording just in case.
Recording in progress.
All right. Oh, let's move over here. Hello, everyone, and welcome back. This is the MHF4U course, Grade 12 Advanced Functions University. And we are just starting it 2. And this is going to be lesson 6, part 1 of 2. So we're going to be spending the next couple of weeks studying trigonometry. And all of you, in fact, deals with somehow as well as a sizable portion of unitary. So we're going to spend quite a time studying things related to trade. We're going to have to worry about actually see it all. What we said we're starting from is trigonometry. Studied before sine, long, cosine. Today as scientific good, that is all. So what are we going to be looking at today? Well, we'll be calculating trigonometric ratios in radians and degrees. There's a couple of key questions in the lesson that deal with this, very friendly. We're going to be calculating angles and ratios formed by points, and then we're going to develop the cast rule. Keep in mind, we're just developing it for now. This lesson has 2 components where we're going to be spending a lot of time using the cast rule, and in fact, that'll be the subject of tomorrow's lesson. Now, I want to develop what we're going to do with this. How do we know things have gone well? Well, for our success criteria, you'll be able to determine the trigonometric ratio given a point. So if I tell you a point in a quadrant, you'll be able to tell me SOHCAHTOA of that given point. Additionally, this is a large set where I'm going to lead step by step through how we're going to be using this. And the method I choose and the ways that we just focusing on formulaic approach because it's much easier from a video perspective to see how I do these things. And it's fairly algorithmic in nature, which is we do this, then this, then this. We should be okay. But for now, let's start with the easy stuff. And I don't often say the word easy math. So here, we're going to evaluate trigonometric ratios. So we got to use a calculator. If we don't have that, then this becomes very hard. But again, use that Desmos scientific calculator. Using each following trigonometric ratios to 4 decimal places. So sine of 25, and we want to be in degrees. So on your Desmos calculator, make sure you click over in degrees. So type in sine of 25. And that's it. That's our answer. So we're going to get 0.4226. And it's worth noting that if I type in second function, 0.4226, I get about 25 degrees. So here, this is the ratio that's with an angle of 25 degrees. The ratio between the opposite and the hypotenuse will be 4.266. I'm going to cover that again in the next section if you forget about what the different ratios mean and so forth. Next one is cos of 72. So we type cos 72. There it is. So we get 0.3090. And we're going to use 4 decimal places because that's what the calculator wants. Last one is tan of 115. We're going to get negative 2.1445. At this point, the question you should be asking, why is this negative? Okay. And that's a question that by the end of today, you'll be able to answer that, why tan of 115 happens to be negative. Sine and cos being positive, like that makes sense. But why is tan of 115 negative? Also, why is sine of 115 positive? Again, these are interesting questions we're going to study. Okay. The second part here, use a calculator to evaluate to 4 decimal places in radians. So make sure you click on radians. That'll change the above answers. Don't worry about that. So now we're going to type in sine of 0.436. So here we're going to get an answer of 0. Let's write this in blue because the other ones are in blue. 0.4223. Cos of 1.257, we're going to get 0.308. And this is going to be a 7 after rounding. And the last one is tan of 2.007. And this is going to be negative 2.1452. It's worth noting that if I type in, say, tan of 4, 4.2, I get a positive number. So here we again get another negative value. And we might be wondering why this number is negative. As it turns out, the reason why C and F are both negative are they're actually both negative for the same reason. So we'll figure out why that is the case in a bit. And so here, I want to take us back to the primary trigonometric ratios. This is what you may people think of when they think of PTRs. So that's going to be our short form for this. We save 1 second on saying it. We think of so, ka, to. So meant sine. Usually it's sine of some angle. It could be sine of A, sine of B. Well, we use sine of theta because it's a typical unknown angle. Is equally opposite over the hypotenuse. Cos going to be cosine of theta is equal to the adjacent over the hypotenuse. I capitalize my A on adjacent typically because my capital A is much neater than my lowercase a. It looks like a 9 inevitably. So just note that that's for teaching purposes. And tan for TOA is tan theta is equal to opposite over adjacent. And your familiarity of this topic, if you've taken the 3U course, you know where we're eventually going to go. But if it's been a long time, typically you've used these ratios to solve for different angles and sides of some triangle. And so if you were given, say, let's use this button instead. There we go. So say you're given a triangle. If this side is, say, 35 degrees, it's a right angle triangle, and this is, say, X, and you know this is 17, you could use a trigonometric ratio to solve for X. So in this case, you would use sine, because sine of 35 is equal to X over 17, and X would end up equaling, in this case, 17 sine of 35 degrees. So if you were curious, you could type that in, 17 sine of 35, it'd be about 9.75. And that's what I trust that if you've taken a course before, like that's what you remember from the past, is that you could use trigonometry for that. So what we're going to use it for is the following. That's going to be a circle centered at the origin, and we're going to say we're going to calculate angles in standard position. And so if I consider a point P, I could drop a perpendicular line, and perhaps I'll write this in blue. There we go. And we have some angle theta that we're calculating. And I'll draw a little arrow in here to say that we're rotating this way. So based on this angle of theta, we know that the height of this triangle is going to be the opposite. The length, perhaps I'll label this in blue for us. This is going to be the opposite. The adjacent will be the horizontal component. And the hypotenuse is opposite the right angle. And please note, I am saying that our hype equals hypotenuse. Was it blue for opposite? Yeah. The op is our opposite. And we're using ADJ to represent the adjacent. Okay. And so what do we know about this triangle? Well, we know that the adjacent is going to be the x component of that triangle, right? So given a point x comma y, the adjacent will be x. The opposite is going to be the height of this triangle, and that'll be y. Now, what is an expression for the radius? Because we can claim that the radius is r for radius. But in reality, the radius is governed by the Pythagorean theorem. So if we take x squared plus y squared, that gives us r squared. This is the basic formula for Pythagorean theorem, but now we're going to apply it to a triangle. Okay, so given a particular point on the triangle, P, which is x comma y, the x component is your adjacent. The opposite, the y component, will be the y component, and the hypotenuse is r, given this condition. It's also worth noting that under these conditions, r has to be at least as great as 0. It's actually impossible to end up with a hypotenuse that's negative. That's because you're squaring two numbers. So if you take 3 squared plus 4 squared, that's positive. Or it can be equal to 0 because, what happens if you have a point right on the x-axis or the y-axis? Okay, and so here, what do we know? Well, in general, sine theta is equal to the opposite over hypotenuse. So what is the opposite? Well, in this case, the opposite is y. The hypotenuse is r. So sine y over r, given a point on the well, cosine theta. Well, that's equal to the adjacent over hypotenuse. So that's going to be given by x over r. And what about tan theta? Tan theta, by definition, is the opposite over the adjacent. So that's going to be y over x. Okay, so this is what we're going to be spending pretty much all of today doing, is studying the different sides of right angle triangles around the unit circle, as well as their corresponding angle. We're going to be covering. Okay, now it's worth noting again, like we're only in the first quadrant right now. In the future, we're going to other quadrants. So right now, right now we are in quadrant 1. But this is true for any point along the quadrant, and we're going to study that step by step. Okay, so let us continue on. And I'll try to maintain my color system as best we can, but I'll probably abandon it at some point. We're going to have a look at quadrant 1. Quadrant 1's the friendly one. So we're determining ratios. Point, which is given by 3 comma 4, is on the terminal arm of an angle theta. Okay, so they're saying that this angle in here, this is theta. Draw the diagram showing theta in standard position. I've taken the liberty of drawing that for us, and then calculate the values of sine theta, cos theta, and tan theta to 3 decimal places. So how did we get that this was 5? Well, remember, this is 5 would be the hypotenuse. The adjacent would be 3, and the opposite will be 4. It's noting that the adjacent is the horizontal component of a point. So typically this is your x value. And the opposite is the vertical component. And instead of the word component, I could use the word part, but component's a better word to describe it. It's slightly more accurate, of a point. And typically this is going to be the y value. Given that this was, say, a point x comma y. The hypotenuse is the radius. And it's under the stipulation that r is equal to the square root of x squared plus y squared. Okay? And so in this case here, r would be equal to the square root of x squared plus y squared. And keep in mind, if this had started off, we could start off by saying that this was r squared is equal to x squared plus y squared, but then we don't want r squared, we just want r, so we take the square root of both sides. So r in this case would be the square root of x, which is going to be 3, and y, which is going to be 4. Okay, so if I take 3 squared plus 4 squared, that's the square root of 25, and the square root of 25 is 5. If you so wish, you could use the calculator to evaluate this all in one step for you, and they'd be happy to do that as well. Okay, so that's how we ended up with a hypotenuse of 5. It's a calculation involving Pythagorean theorem. So we drew the diagram, and now we want to calculate the values of sine theta, cos theta, and tan theta. Okay, so we will start off by writing sine theta is equal to the opposite over the hypotenuse. So in this case, we're saying that sine theta is equal to the opposite, so that's going to be 4, over the hypotenuse, so that's going to be 5. Great. We're going to worry about 3 decimal places afterwards. Cos theta is equal to the adjacent over the hypotenuse. So that means cos theta is equal to the adjacent, which is 3, over the hypotenuse, which is 5. And tan theta is equal to the opposite over the adjacent, which means that tan theta is equal to the opposite, which is 4, over the adjacent, which is 3. And if we need to, we can make this decimals the 3 decimal points. So 4 divided by 5 would be 0.800. 3 divided by 5 is 0.6, but again, it wants 3 decimal places, so we'll put those in. And tan theta is 4 divided by 3, so that's going to be 1.333 repeating. So what's the relevance of this? Well, I'm going to do the calculation first, and I'm going to write out the result. So sine theta is equal to 0.8, cos theta is equal to 0.6, and tan theta is equal to 1.33. So if you notice here, I'm going to type in inverse sine of 0.8. And I got to get some, and this is going to be the angle that's in there. So it's like a 53-degree angle. And we're going to be working in degrees for the moment. Eventually, we're going to switch over to radians, but for now, we're just going to use degrees because it's easier to think about. Second function cos is going to be, we're going to do 0.6. And again, you can put those extra zeros, that doesn't matter. We get 53.13. Oh, we got the same number. And if we do second function tan, and we do 1.333, we get almost the same number. We get pretty close, but then you're like, oh, we rounded, right? Is that the problem? It is. If I include some more 3s, the answer becomes more accurate. So it makes sense to use the fractional component and write this as 4/3. And so we end up with this statement that if I take the second function of 4/5, that's equal to the second function cos -1 of 3/5, which is equal to inverse tan, or tan -1 of 4/3. Ooh, that was an awful 3. Let's try that again. In that these all equal about 53 degrees. And so given an angle theta and a triangle, if you happen to know all 3 sides, you could use sine, cos, or tan to figure out what that angle of theta must be. So any of these would work, and typing these all into the calculator, because that's what the the question was trying to get at was that if you wanted to test to see what the angle was, you could do that, and that's fine as well. Okay, so we're done. This extra part here, this was bonus. This was a bonus component. But again, I wanted to include that here for us just to state that the angle theta is equal to all of those together. So theta can be determined 3 different ways so far. Okay. Let's back reading here. Okay. The P negative 1 comma 2. So let's go ahead and sketch this out. Okay, there it is. So the point P, which is on the terminal arm of an angle theta. Draw the diagram showing theta in standard position, and then calculate the values of sine theta, cos theta, and tan theta to 3 decimal places. So it's exactly the same as this question, except now we're not going to be in quadrant 1. So let's have a look. So let's work in purple, I suppose. Okay, so the point negative 1 comma 2. So this is negative 1. This is 2. So it's about here. So this is the point P, which is given by negative 1 comma 2. Traditionally, this is how you would draw this point. My recommendation would be just to sketch the point, and then we can drop a perpendicular line and connect it to the origin, like so. And so now we can say that the horizontal component here is negative 1, and the vertical component is 2. Now, the angle we're talking about here, let's work with pink. Is pink okay? Yeah, pink should be fine. The angle that we're talking about is this angle. This is the angle theta. And you can see theta is already greater than 90 degrees. So we know theta is greater than 90 degrees, but less than 180. So a good way to describe that would be theta is between 90 and 180 degrees. How do we know it's 180? Well, because keep in mind, a straight line has an angle of 180 degrees, and if it's a corner, we know that it's at least 90 degrees. Okay. And you might be thinking, this terminology kind of sounds familiar. Did we talk about this recently? We did. The last lesson is where we started talking about angles in different quadrants. This is part of where we were going. Okay. So what do I know about the radius r? Well, r is subject to r squared is equal to x squared plus y squared. That doesn't change. And so r will be equal to the square root. The x component is negative 1. The y component is 2. So if I take on my calculator here, negative 1 squared, we get a positive number. And if I take 2 squared, we get 5. So r would be equal to the square root of 5. So here we're going to say that r is equal to the square root of 5. And so now we can actually label our corresponding sides. So based on the angle of theta, okay, the x component is always the adjacent. The y component is always the opposite. Okay, and if I was going to label this, remember the point P is x comma y, like so. Okay. And then the hypotenuse is going to be this square root of 5. So this will be, okay. So just like before, we go through this step by step. Sine theta is equal to the opposite over the hypotenuse. So for us, this means that sine theta is equal to, what's the opposite going to be? Well, it's going to be 2. What's the hypotenuse? It's going to be the square root of 5. This is where the 3 decimal business comes up. In our class, we're quite happy with this, but the textbook does insist on making this into 3 decimal points. So we'll go ahead and calculate that afterwards. Cos theta is equal to the adjacent over the hypotenuse. And so for us, this means that cos theta is equal to, now the adjacent's a negative number. Can we write that? Sure. So we write it as -1 over the hypotenuse, which is the square root of 5. And tan theta is equal to the opposite over the adjacent, which means for us, tan theta is equal to the opposite, which is 2, over top of the adjacent, which is -1. And so now, let's go ahead and just calculate these down. So if we take 2 divided by the square root of 5, we get this number. So we're just getting the decimal representation. So this is 0.894. Cos theta, we've got here -1 divided by the square root of 5. So this will be -0.447. And if we do tan theta, this is just going to be -2. And if you want to, you can put the extra zeros in there. So we are done the question. But now I would like to determine the angle. Okay, so let's do, and I'm not going to write a bunch of equal signs here. So let's do inverse sine of 0.894. Let's do second function, inverse cosine of -0.447. And let's do inverse tangent of -2. And this is the interesting part. So if you notice, we appear to have some concern here, because when we tried to do the inverse sine, we ended up getting 63.38. So we got about 63.4 degrees. When we did inverse cosine, we got 116. That appears to be legitimate because our answer has to be between 90 and 180. And when we tried to do tan, we got a negative answer of all things. And so here we end up having some concerns with respect to how could you possibly calculate what the angle is going to be. And that's going to be the study of today's lesson, is how do we figure this out? Because here, these should all be equivalent answers with respect to solving for the angle in quadrant 2. And yet, we have 3 completely different answers. If you wanted an answer to trust, the answer to trust for this particular instance would actually be theta is equal to 117 degrees, rounded, of course. So I'll write that theta is equal to 116.55, which is equal to about 117 degrees. So we know that that's going to be the case, because we know theta has to be in quadrant 2, and this is the only. But again, we're going to study all this components later. For now, I just want to be able to write down the ratios, and then we're going to talk about how to interpret them in a bit. Okay, letter C is similar situation. Now we're talking about the point P, which is given by 4, -5, and we're going to do the exact same thing again. Okay. Oh, I don't want to click that button. Let's go with black, and let's sketch this in. Okay, so now we have the point P is now 4, -5. So that's going to be, sorry about that. Thought I silenced my phone. Okay, 4, -5 is going to be down here. So this is the point P, which is given by 4, -5. And again, like what we did before, we drop a line to we drop a horizontal line to the x-axis, and we want to create our triangle. Not bad. Okay. All right, so what do we know? Well, the horizontal component is going to be the x value. So that'll be in, what color did I use for that? Green. Okay. So the horizontal component will be 4. The vertical component will be -5. And what about r? Well, remember, r is given by the square root of 4 squared plus -5 squared, which is going to be 16 plus 25. So that'll be the square root of 41. So r will be the square root of 41. 4 will then be the adjacent. 5 will be the opposite. And the square root of 41 will be the hypotenuse. And the angle that we're going to concern ourselves with will be this one. We're going to go all the way around to here. So this is the angle theta. And so what do we know about theta? Well, theta happens to be an angle in quadrant 4. So we know that theta will be between 270 and 360 degrees. Well, because it's in quadrant 4, it goes all the way around. And so let's go ahead and calculate these. And again, for the purposes of brevity, we're going to, so TOA, we'll just write that out in advance here. So sine theta will be the equal to opposite over hypotenuse. This time around, the opposite is -5. So this will be -5 over the square root of 41. And again, we'll have to put that round to 3 decimal places thing. So we'll do that afterwards. Cos of theta is equal to the adjacent. So this will be 4 over top of the square root of 41. And tan theta will be the opposite over the adjacent. So that'll be -5 over 4. And so, figuring this out, if I take -5 and divide it by the square root of 41, I get -0.781. If I do 4 divided by the square root of 41, I get 0.625 after rounding. And if I do tan, 5 divided by 4 of the negative variety, this will be -1.25 with a 0. And I'll just put the negative in here in case you're following along on the calculator. So now we actually have a profound problem. So we know the answer should be between 270 and 360. We studied that on the lesson of 2 times ago. But unfortunately, when you go to type these things in, well, that's a negative answer. That doesn't seem to be quite right. Cosine -1 is 0.625. Well, that's a positive answer. That doesn't make any sense because the answer should be 360. And if we do tan inverse tan of 1.250, we also get the same, answer. We get another 51.34, but it's going to be positive instead. And these answers here would all be the same, except they differ by sign. But remember, we ended up rounding the square root of 41. So that's why they're slightly off. So here, none of these answers seem correct. So this seems to be a bit of a problem, right? Because we know that the answer has to be 360, because if we're talking about an angle, the key point is, in standard position, this would then imply that the angle should be between 270 and 360 because it's a quadrant 4 angle. So let's try to study how we can figure this out. So how do we make, because I've provided that there's a problem of some kind. We don't have a method yet to calculate that point exactly. You might be looking at this video and thinking the answer is 309. You'd be correct, but we'll study why that's the case. So here, Well, let's consider the following. So when we reflect the point 3, comma 4, so we studied this earlier, into quadrant 3, it becomes the point -3, -4 with corresponding ratios. So those corresponding ratios would be sine theta would be, now keep in mind, this is -4 as the vertical component, -3 is the horizontal component if it's x and y. So the opposite, and the hypotenuse is still going to be +5, right? That doesn't change because of Pythagorean theorem, right? So keep in mind, r would be the square root of -4 squared plus -3 squared, and this is still 41. 41. Oh, not 41. 25, which is 5. So that part doesn't, I was thinking of the above question. That does not change. Okay, so what about sine theta? So sine theta is going to be -4/5. Cosine theta is the adjacent. And so keep in mind, we were talking about this angle here. This is the theta we're interested in. The angle theta appears to, the adjacent in this case is going to be -3/5. And tan is the opposite over the adjacent. So that's going to be -4/-3. Because remember, this is the opposite. This is the adjacent. Here's our hypotenuse. But you have a negative divided by a negative. So that's a positive number. And already, we actually can't figure this out using normal methods. Because just like before, if I try typing in right now, negative sine of 4 divided by 5, I get a negative answer. If I typing in second function cosine of -3 divided by 5, I get this answer. And if I try typing in inverse tan of 4/3, I get a positive. I have 3 completely different answers again. But, and here's the important part, we know that theta should be between 180 and 270. But why did we reflected the point? So what was the importance of that? And the reason for that is, let's pick this gold color, I suppose. Here, this angle of theta is exactly the same size, magnitude-wise, of this angle of theta. Those are both the exact same length. If you remember from earlier, we said that length was 53 degrees. I'm just scrolling up to the top for your benefit. Here. So here we said that angle was definitely 53 degrees because it was in the first quadrant. We all agreed that was the case. And so we know that this gold point, theta, is 53 degrees. Ooh, I like that gold. I'm going to save that for all lessons now. So what do we know about this angle here? Well, the quadrant 3 angle, which we'll call, say, theta 3 for the moment, we know that it's going to be 180 degrees plus that gold point. So the angle theta is going to be 180 degrees plus the gold angle, which was what we call 53 degrees. And so when we add those together, we get 180 plus 53, we get 233 degrees. And so now, if we type in sine of 233, cos of 233, and tan of 233, you notice that these answers correspond pretty close to their answer. So -4 divided by 5 is about -0.079. Again, we had to round the decimals, that's why it's slightly off. Cos of 233, -0.6. 4 divided by 3 was that 1.33 number. It's pretty close to that. And so somehow or other, we actually landed up with the right answer. We just needed to use this gold answer, the golden reference angle is what it's going to be called. And so, just as a little note, we want to be using something called the reference angle to figure that out. Because I've already shown you that when you try to calculate the angle in the different quadrants, other than quadrant one, they end up being different. Because in example A, we got the same thing because they were all the point was definitely in quadrant one. In example two, it seemed cosine was the only one that worked. And in examples in letter C, none of them worked to get our right answer. But yet, we were able to use the quadrant one angle to determine the quadrant three angle. And so that's going to be our method for solving these is we're going to be determining a reference point, which will be our golden angle, our reference angle, and using that to figure them out. And so in general, for any, and we call this principal angle greater than 90 degrees, the value of the trigonometric ratios are either the same as or the negatives of the ratios for the related acute angle. The related acute angle was what we called our reference angle. These relationships are based on angles in standard position in the Cartesian plane and depend on the quadrant in which the terminal arm of the angles lie. So if you notice, the reason why sine and cos were negative in quadrant 3 was because the adjacent and the opposite are both negative in those two quadrants. Whereas for tan, the reason why it's positive is because you took a negative divided by a negative, and so forth. So we're going to study this quadrant by quadrant and go through this. So we're going to develop the cast rule now, and that's going to take us to the rest of class with one follow-up example at the end. We will now develop the cast rule quadrant by quadrant. To help in distinguishing the angles in different quadrants, we will call an angle in quadrant 1, theta 1, an angle in quadrant 2, theta 2, an angle in quadrant 3, theta 3, and an angle in quadrant 4, theta 4. So in quadrant 1, this is actually okay. So here in sine of theta 1 is equal to y over r, cos of theta 1 is equal to x over r, and tan of theta 1 is equal to y over x. All of these ratios are positive. And so we can use any of the ratios and know that all three of these ratios are positive in quadrant 1. So all PTRs, or primary trigonometric ratios. So we'll say that all primary trigonometric ratios are positive because the x component is positive, the y component is positive, and the radius is positive. You can also use like an individual example, say we were talking about the point P, which is given by 4, 3, and the radius would then be 5. This is a Pythagorean triple, 3, 4, 5. You could also just use an individual point to help kind of think about this. And so here in quadrant 1, all the ratios are positive. Great. Sounds good. Let's continue on. What about quadrant 2? Well, in quadrant 2, sine of theta 2, because now we're talking about an angle in the second quadrant, is equal to y divided by r. So the height is still positive. So sine happens to be positive. There you go. Cosine of theta 2 is equal to negative x over r. Well, since we've got a negative number here, that means our ratio will be negative. And tan of theta 2 is y over negative x, because remember, this value will now be a negative x value. And again, if you want to think about an individual point this could be the point P comma negative 3 comma 4, where the radius is 5. Okay? Because again, I'm just using just the description given here. And tan will also be negative. So it seems like that in the second quadrant here, we have just sine is positive in quadrant 2. The other two ratios are negative. What about quadrant 3? We don't have a unit circle this time. I just happened to because the diagram I found online, I couldn't find one in quadrant 3. These things happen. So sine of theta 3. So this is an angle that's going to be in quadrant 3. The y component is going to be negative because that's all we know, that we know for sure it's going to be negative. So here, you might think of this as a point of, let's see, this is going to be 1, 2, 3, 4, 5, 6, 7, 8. So this looks like 8 comma 6. This looks like the point 8 comma negative 6. So the radius will be 10. Okay, so here this is negative 8 and negative 6. You can think about it that way, but in general, here sine of theta 3 is negative y over r. So this ratio will be negative. Cosine will also be negative. But as we saw from earlier, when you take negative y divided by negative x, this ended up just becoming y over x. So tan of theta 3 happened to be positive. So in quadrant 3, just tan is positive. Okay. And lastly, but not leastly, in quadrant 4, so now we're talking about theta 4, so an angle in the fourth quadrant. What do we know about this? Well, the y component's going to be negative because we're going down, but the x coordinate will be positive. So this point P will be given by 3 comma negative 4, if you want like a kind of a way to think about it. So here, theta comma 4 will be negative 4 divided by y. So sine will be negative in quadrant 4. Cosine is going to be positive in quadrant 4. Why is that? Well, the x component's positive and the y component's positive. And then tan of theta 4 will be negative. Okay, so here what we just did was we had a look at all of the different values that the ratios could take. So now let's go back and talk about the angles themselves. So we talked about the ratios. Let's write this one in green, I guess, so we can make sure it all lines up. Okay, so back to example 1. So in example 1, we know that the angle's in quadrant 1. So for quadrant 1, theta will be between 0 and 90 degrees. That's not too shocking to figure out. And we can see that that's the case because it forms a right angle. So it's between 0 and 90. Great. What about quadrant 2? So here, if we have a quadrant 2 angle, we know theta has to be between 90 and 180. Because again, a straight line is 180 degrees. But how do we figure out this angle? Well, remember, we have our golden point, the reference angle, and we can figure what out that's going to be in quadrant 1. And so we know that to figure out a theta 2 angle, that's going to be equal to 180 degrees because it's an entire straight line, except the golden angle, the reference angle, which will be our theta 1, right? So if we have theta 1 in the first quadrant and we reflect it over, then that means we can figure out theta 2 by just determining the angle in quadrant 1 and then subtracting it, just like what we did for our example. We could figure out the angle in quadrant 3 because we just used the positive version in quadrant 1. And so if we have the quadrant 1 angle, we could just take 180 minus the quadrant 1 angle. Similarly, for quadrant 3, you can see that we've got this reference angle in here again, theta 1. We know that in quadrant 3, theta is going to be between 180 and 270. But to figure it out, we can just take 180 degrees plus theta 1. Just like before. And lastly, for for the last one here, we have there's our reference angle in there. We know that in quadrant 4, theta has to be between 270 and 360 degrees. And so in quadrant 4, theta 4 is going to be equal to, it's the entire circle, 360 degrees, minus theta 1, the reference angle. And so we're going to summarize our results. So in quadrant 1, so importantly, theta 1 is the reference angle. It's going to be between 0 and 90 degrees, or between 0 and pi on 2. So that's the reference angle. In quadrant 2, just sine is positive. So theta 2 is going to be 180 minus the quadrant 1 angle, and it should be between 90 and 180. Okay. Or if you're thinking in terms of radians, theta 2 will be pi minus theta 1, where it's between pi on 2 and pi. So I just wrote both versions here because it's easier to think about this in degrees and then translate this to radians afterwards. In quadrant 3, just tan is positive. And to figure that out, we take theta 3 is equal to 180 plus theta 1. So it's going to be between 180 and 270. And to figure out this in radians, we just take pi plus theta 1. I'll fix that in the notes afterwards. And it has to be between pi and 3 pi. And lastly, in quadrant 4, theta 4 is equal to 360 minus theta 1. So it has to be between 270 and 360. So theta 4 in radians will be equal to 2 pi minus theta 1, or between 3 pi over 2 and 2 pi. It's worth noting that 3 pi divided by 2, so this is going to be 4.71. This is 6.28, and pi is 3.14, and pi over 2 is 1.57. Okay, so that's the CAS ratio and how we can use the reference angle to determine the angles in different quadrants. And so in above all these in the above for all of these cases, we can use the quadrant 1 angle called the reference angle to determine angles in different quadrants. Okay, so the point 3 comma negative 3 comma 5 is on the terminal arm of an angle theta. Draw the angle in standard position. So let's do that. So we're going to draw the angle in standard position. And we want negative 3 comma 5. So that's going to be up here somewhere. So this is the point P, negative 3 comma 5. So the vertical component is 5. The horizontal component is negative 3. And there it is. So there it is. There's our point in standard position. Do we need the hypotenuse? Not yet. Doesn't say that we need it yet, so we'll just ignore it for now. But this is the angle of theta we're interested in. So it's going to be a quadrant 2 angle. But they want us to first determine the reference angle. Okay. So here it's worth noting this 5 will be the opposite. The negative 3 will be the adjacent. So we'll just use the positive version. So we'll just reflect it back into quadrant 1. So we'll just consider this ratio instead. So here we're going to use the reference angle. So that'll be tan of theta 1 is equal to the positive version of this. So 5 over 3. So remember, we're considering TOA. So theta 1 will equal the inverse tangent of 5 over 3. So if we take 5 divided by 3, we get 59 degrees. But we know the answer has to be in quadrant 2, right? So to determine the angle theta, we can just take 180 and minus theta 1. And so the angle in the second quadrant will be 180 degrees minus the reference angle. And so if I take 180 degrees minus 59, I get that the angle in the second quadrant should be 121 degrees. So here, that is the angle that's going to be formed by this triangle. And so that's going to be it for us for today. Tomorrow, we're going to solve lots of these ratios, many of them. And so we're going to come prepared with our chart. We're going to make heavy use of this chart throughout the lesson, but we're going to be solving lots of questions that look like this and actually lead to multiple answers. As always, if you have any questions or comments, please feel free to reach out and we'll get back to you as soon as we can. But for now, please have yourselves a great day and goodbye for now.